Lesson 6.4 takes our random graphs that we did in the last lesson, exponential functions, and turns them into real world problems called growth and decay. Let's talk about exponential growth first. It occurs when a quantity increases by the same factor over time. Remember, the factor is what we're multiplying by. And so we've got this general formula. And they tell us a is greater than 0, r is greater than 0, then it's called an exponential function. So here's what the pieces mean. Y stands for the final value. R stands for the rate as a decimal. Sometimes it's a percent, and then you have to turn it into a decimal. A is the initial amount, and T stands for time. Typically it's in years, but occasionally it's not, and then they would tell you in the story. The expression 1 plus r is called the growth factor. So let's use this in an example. The inaugural attendance, which means like the beginning attendance when it first started, of an annual music festival is 150,000. The attendance Y increases by 8% each year. So letter A, write an exponential growth function that represents the attendance after T years. So we just kind of plug the pieces in. So it's going to start with Y equals. The initial amount is 150,000. Don't put commas in an equation. And then we are multiplying by 1 plus r, which is the rate as a decimal. So that's 0.08, and that's raised to the t because they tell us t years. What we should do, though, just to wrap it up, is 150,000 times 1.08 to the t, because we should add to kind of simplify the parentheses. But what you can't do is multiply these two values because exponents come before multiplication. So this is as simplified as it gets. Then in letter B, they want us to use that equation to figure out how many people will attend the festival in the 5th year. So I'm going to plug in 5 for my t value. So it's going to be 150,000 times 1.08 to the 5th. So you do 1.08 to the 5th. You got to have your calculator. And I get 2.44888 times 150,000. And that gives me 367,332 people. Obviously, I'm going to round to the nearest whole number, right? Because you can't have a decimal person, but it says you actually have to round to the nearest 1,000. So the thousands is right here. So it would be 367,000 people. If you don't round, technically, you're wrong. Very similarly, we have something called exponential decay. And that's very similar to growth, but it occurs when a quantity decreases by the same factor over equal intervals. So you can see in the formula, it's very similar, but instead of addition, we have subtraction. But all the things mean the same, and again, obviously then 1 minus r would be the decay factor. So here in example 2, we have to determine whether it shows exponential growth, decay, or neither. So we're looking at what it's multiplied by, or divided, right? So this is being, let's see, that looks like divide by 3. So then since it's being divided by the same number, then it's exponential decay because it's going down. And here, that's times 2. All right, so then this is exponential growth because it's being multiplied by the same number each time. Now you can look at an equation and very quickly tell whether it's going up or down, whether it's growth or decay, based on that growth factor or the decay factor. So this piece right here, which would be 1 plus r, is greater than 1. So that means that r was, positive, so we can add it. So 1 plus r is 1.07, so that means that r must have been 0.07, which tells us that since we have to identify the percent, that was 7%. So it's growth because the value is greater than 1. In this equation, our growth factor is less than 1, which means it's not a growth factor, it's actually a decay factor. So if 1 minus r is 0.98, then r must be 0.02. which means that my decay factor is 2%. So it's going down 2%. This one is going up 7%. In the interest of time, let's skip example 4 and look at compound interest, which is a real-life skill that happens in real life in banks. So when you first learned about interest in math class, they were like, oh, you get 2% interest. So you find 2% and then you add that value every year. But that's not how banks work. What happens is they add the interest into your bank account, and then when they recalculate the interest every month or year or quarter, whatever they do, then that money is now part of your bank account, so you get interest on the interest. It's not usually a lot of money, but it accumulates over time. Whereas what you learned about a few years ago when you learned interest, which was called simple interest, you do not accumulate that. So we've got a crazy formula, but they tell you what all the parts are. And let's use that to answer a question on the next page. You deposit $100 in a savings account that earns 6% annual interest compounded monthly. So I've got $100. It's earning 6% annual interest, and it's compounded monthly. Those are important things if you look back at the formula. And then we have to write a balance after t years. So the first thing that we're going to do is look back at our formula. And we need to know P, which is the initial amount. So they tell us that is 100. All right, first piece down. Now the next piece is 1 plus r over n. R stands for the rate as a decimal, so that's 0.06. And n is the number of times it's compounded. So this is compounded monthly, so that's 12 times per month. So every month they recalculate my interest. So that's what compounded monthly means. Then the next step is to do n times t, so that'd be 12t as my exponent. You should reduce your parentheses, so I get 100 times 1 plus 0.06 divided by 12 is 0.005 to the 12t, so that is 100 times 1.005 to the 12t, and that is my value for y. So if at any point I wanted to figure out how much money would be in my bank account, I would plug this into the formula. If I wanted to know how much interest I would accumulate, I would then subtract out 100 to figure out how much money got added into the bank. In example 6, the table shows a balance of a money market account, which is another type of bank account, over time. We have to write a function, and then we're going to graph it. So how do you know what the growth factor is, right? You have to figure out what it's being multiplied by. So you kind of do division to reverse the multiplication. So what you do is you say 110 divided by 100, and you figure that out. As 1.1. And then you can just confirm with like another point, right? Do 121 divided by 110, and you get 1.1, so you can double check that it is 1.1. So that's the growth factor, which means it's going up by 10% every time. So that would be y equals 100, because that's the initial amount, times 1.1 to the t. Now, to save time, we're going to skip the graph, but what you would do is you would graph these values, you would make a chart, for example 5, graph those values, and then kind of see how the balances compare. All right, we got one more example to do. In example 7, we've got a car, and it starts at $21,500, and it loses 12% of its value each year because cars depreciate over time. Write a function that represents the value of the car after t years. So we know it's going down, so it's going to be a 1 minus r equation. So it's y equals the initial amount, 21,500, times 1 minus 0.12 to the t. So then that becomes y equals 21,500 times 0.88 to the t. In letter B, we want to find the approximate monthly percent decrease in value. So what we need to know is what number multiplied 12 times is 0.88. So what we're going to do is we're going to find the 12th root of 0.88. What? I thought I didn't have to remember old lessons. Never. So the 12th root of 0.88 is 0.989. So if 1 minus r equals 0.989, that means that r is 0.011, which is 1.1%. Now, the reason that you can't just do divided by 12 is because it's not linear. If it were linear, you could just say, hey, divide by 12, it's the same every month, but it's not. Multiplication and growth rates don't work like that, so we have to do it this way. In letter C, we have to graph the function and use the graph to estimate the value of the car after 6 years. Now, I know we've skipped a lot in this lesson. I've skipped over the non-essential skills, but we're going to skip letter C because I don't want to make this video longer than it needs to be. If you want to go and you want to do any of those things that we skipped, you are more than welcome to, but I think you get the overall understanding of exponential growth and decay. If you have any questions, write them down and ask me when you come to class.